Welcome to UVU CS3060 Lecture 10.4, where we discuss various page replacement algorithms. So the first algorithm we're going to talk about is the first in, first out algorithm. Yes, this sounds very familiar. You'll hear it again when we get to file systems. First in, first out is going to take our reference string. This reference string is not going to change for all of our algorithms. So we'll use this consistently across all the different algorithms. For our particular purpose, we're going to have 3 frames of physical memory. Now this seems small, but this is just for demonstration purposes. So with this particular reference string, what we're going to do is we're going to use this reference string and populate our page frame. And everywhere there's one of these blue boxes, we have a page fault because a page was accessed without actually being physically in memory. So we start with 7. And that's one page fault, and we fill one entry. In the first in, first out algorithm, when a particular access happens, we just simply load the next frame of memory with that page. And right now we're just loading in empty frames. So this is fine, 7, 0, and 1. But now we come to the page access to 2. Well, we've already filled our frames, so what page will we replace? This is first in, first out. So we go back up to the top of the list and we swap out 7 for the number 2. Now there is no page fault for this access to 0 because 0 is already in memory. So no page fault. We've only got 4 page faults so far until we access 3. First in, first out tells us that we need to swap. We just did 2. Now we need to do the next one, which was this page 0, and we swap 0 out and write in page 3. Now, first in, first out doesn't know anything about what's going to happen. It only knows about what has happened. Thus, it has no idea that the very next page access is going to be to page 0, or else maybe it wouldn't have swapped that out. But this is first in, first out. So what we do is when the 0 access causes a page fault, we swap out page 1 and swap in page 0. Page 4 is accessed, and we simply go back to the top of the list, swap out page 2 and swap in page 4, which again is a bad decision simply because this 2 is going to access next. But we go ahead and put the 2 in here. Then we have an access to 3, which just barely got eliminated. Then we have an access to 0, which just barely got eliminated. Fortunately, we stopped doing that, and we access 3, which is there, and 2, which is there. And then 1 is accessed. Well, again, we're just simply following this first in, first out, so 1 gets placed in the next spot. And so we have an access to page 2, which replaces 3 here. Then we have an access to 0 and 1, which do not cause a page fault. But then an access to page 7, then an access to page 0, and finally an access to page 1. The final state of our frames is in order 7, 0, and 1. So hopefully you were able to see that there is quite a bit of inefficiency in this first in, first out algorithm. It is not uncommon for pages to be swapped out that may get swapped in very soon or maybe immediately afterwards. So first in, first out is a simple algorithm, but is also very inefficient. Now, we've had, in the course of this, we've had 15 page faults for this particular reference string. We need to remember this 15 page faults because it's going to be used as a value of comparison with the other algorithms. Now that value of comparison, the page faults, actually can be misleading because of something called Belady's anomaly. So we're going to temporarily use a reference string here, this 12 value reference string. And let's go ahead and run this reference string through first in, first out, using 3 frames. So 1 causes a page fault, 2 causes a page fault, 3 causes a page fault, 4 causes a page fault, 1 causes a page fault, 2 causes a page fault, 5 causes a page fault, 1 and 2 do not cause page faults, but 3 does, then 4 does. And the final state of our particular page frame is 534. So perhaps we can solve this problem by going to 4 frames. Well, if we take a look at the 4 frame solution, we have a page fault at 1, 2, 3, and 4. 1 and 2 do not page fault because they're in memory. But then 5 page faults. Then 1, 2, 3, 4, and 5. All of these are page faults. Increasing the number of frames has increased the number of page faults to 10. This is called Belody's anomaly, where you're not always guaranteed to have less page faults when you increase the number of frames. So it's important to realize that while we use this page fault value for comparison, it is not always the most accurate measure that we can use. And you can see here, if we had, with that particular previous reference string, we have 1 and 2 frames, which cause 12 page faults. Then we come down here to 3, which caused 9. And then 4 frames went to 10. And then finally, if we just simply have 5 frames, it's going to be consistent. We'll just simply load those 5 frames and then continue on. So Belody's anomaly can show that with certain reference strings, we can increase the number of page faults even if we increase the number of frames available. So let's consider for a moment an algorithm where we can actually evaluate what's going to happen, the page references that are going to happen in the future. So let's go ahead and take this same reference string, this 701203 reference string, and we're going to run an algorithm that's going to look ahead and determine what page is going to be accessed the latest, so that particular page can be loaded. We want to keep pages in that are going to be accessed soon. So we start with 701. Those are 3 page faults. You will always have those initial page faults as the page table is loading. But now we have a page fault on 2, and we have a full list of frames. So this page fault here, this number 2, needs to go in someplace. Where will it go? Well, what we do is we look for 7. 7 is way over here at the end. We look for 0. That's actually the next reference. And then we look for 1. And 1 is over here, but 1 comes as accessed before 7. So we're going to keep 0 and 1 and throw out 7. So we put page 2 in place of 7. Now we have the 0 access, which is good, but 3 causes a page fault. So let's look ahead again. So right now our page frame, the page frames is 201. So which one of 201? We can see 0 is next, and we can see 2 is pretty close, but 1 is way down here, which means 3 will replace page 1. Notice we've deviated from first in, first out. Now, instead of just simply going to the next element in the frame, we actually overwrite the particular frame that's going to be accessed the latest. So 3 replaces 1, 0, no page fault, 4. Which one are we looking for now? Well, we have 2, 0, and 3. So if we take a look ahead, 2 is next, 3 is next. So 0 is the page that's going to be accessed the latest. So 4 replaces 0. And we continue. We have success, we have a hit, and then we have 0. So which one does 0 replace? Well, 0 is we have 2, 4, 3. Here's a 3 and there's a 2. meaning that we're not going to replace 2 or 3, we'll replace 4 with 0. You can see that we're bouncing back and forth between 0 and 4. Then we continue with accesses. 3, 2, and then we have an access to page 1. So which page do we replace? Well, our frames are 2, 0, and 3. We look at our reference string. 2 comes next, and then followed by 0. That leaves 3 that needs to be replaced. So we replace it with 1. All right, 2, 0, 1, all hits, and then 7. Well, 7, we look ahead. Which one needs to be replaced? Not 0, not 1, because those come next. So we replace 2 with the number 7. So in this particular example, using an optimal algorithm, we find that 9 is the optimal page faults for this algorithm compared to the 15 that we had with first in, first out. Here's our problem. We are using a magic looking glass algorithm here. We can see into the future with this algorithm, which frankly the prophecy attachment to most computers is not available quite yet. This algorithm is optimal and is a good algorithm to compare to see what the minimum number of page faults will be for a certain number of frames. Is not practical. We cannot look into the future. So while this algorithm is not an algorithm that's used in operating systems, it can be used to help identify how well an algorithm is performing. Our last algorithm is called the least recently used algorithm. Now, instead of using future information, least recently used will use past knowledge. It's basically looking backwards and determining whether or not a page was recently accessed to determine if which one should be replaced, which one will be the victim frame. So let's go ahead and run through this and let's look through the past. So 7, 0, and 1 are the first 3 page faults, but then we have a page fault at 2. Which one's the least recently used? Well, if we go backwards, 1 was used and 0 was used, so 7 is the least recently used, thus 2 replaces it. 0 gives us a hit, and then 3. Well, let's look backwards. If we're trying to replace a frame with a 3, what was the least recently used? Well, there was a 0, there was 2, so the least recently used is 1, so we put 3 into the place of 1. Now we go ahead and 0 is accessed, 4 causes a page fault. So let's look backwards. Our frames are 2, 0, and 3. We look backward from 4. 0 was accessed, and 3 was accessed, leaving 2. Once we found the one frame that's not part of these most recently used accesses, we can replace it. So we replace 2 with 4. Now, you can see by the next access that least recently used is not always the best. So now we have 2. Well, 2 needs to replace a particular frame. We look backwards. We have 4, we have 0, so we need to replace 3. So we put 2 in place of 3. Well, what's the next access? 3. So we look backwards, we see 2 and 4. So we don't replace 2 and 4, we replace 0 with 3. Of course, the next access is 0. So where do we replace 0? Well, let's look backwards. We have 3 and we have 2. So 4 needs to replace with 0. Fortunately now we have a couple of hits, 3, 2. Now we have 1. Which one do we replace? Well, we look backwards. There's 3, there's 2, then there's 3. So we replace 0 with 1. We have a hit, and then we have 0. Well, 0 is going to replace 3 because 1 and 2 are the most recent. 1 is a hit. 7 is then requested. 7 is going to replace 2, and then we go 0, 1, which are hits. So optimal gave us 9 faults, whereas FIFO gave us 15 faults. This particular algorithm, least recently used, causes 12 faults. This is generally a good algorithm, even though it has its weakness. So the question is, how do we implement something like least recently used? How do we make it so that we know which particular frames were least recently used? Do we keep this particular reference string in memory to be able to look backwards? There are better ways to do this. So one way to manage this is to have a entry in every page table, or every page table entry has a counter, and every time a page is referenced, you will copy the clock into this counter. So the clock value of the CPU will be put in the counter, and then what you'll do is you'll look for the counter that has the smallest value or the oldest value, and that's the victim. One of the real tricks here is every time a page is referenced. So the memory management unit has to support copying the clock into that page table entry. So it may be a little inefficient. We can use a stack. Basically, keep a stack of page numbers that's in a doubly linked. If a page is referenced, move it to the top. This, of course, would require 6 pointers to change, and of course, because it's a page reference, meaning that an instruction accessed that particular page, this has to be supported by the memory management unit. So the nice thing about this particular algorithm is that we don't have to search for a replacement. All we have to do is take the top element off the stack and replace that, or the bottom element of the stack and replace it. We see that both LRU, the least recently used, and optimal algorithms were cases of stack algorithms that don't have Belady's anomaly. So again, if we have at point A, our stack looks like this, 21074, and we have a memory access of 7, then this 7 entry is moved to the top of the stack. And what we do is we replace using the lowest value. The thing is, for least recently used, we need special hardware. And we've seen that there's stack algorithms that may require special hardware to operate. Memory management units tend not to be terribly complicated. And so it's best if we use something simple. One way we can do this is have a bit in our page table. Each entry is associated with a bit that is set to 0, meaning that page has not been referenced recently. When a page is referenced, the bit is set to 1. And what can happen is after whenever a page needs replaced, we just simply scan through the reference bits to find 0. The thing is, how do we order this? Are we always just simply going to take the top one that's 0? That may be terribly inefficient when we perform that replacement. There's also a way to do this called the second chance algorithm. Second chance is where we have we go through the list of pages that can be replaced or have been referenced in a circular manner, meaning that we don't just simply start at the top of the list and pick the top one that has a bit of 0. We work through in a clock type of manner. Here's a diagram that shows this. So let's say, for example, we have an access to we have this pointer that is pointing to a reference page that has been referenced. Well, the thing is, whenever whenever a page fault happens, this pointer is moved forward until a 0 is found. And if this page has been replaced, it will the page will be put into here. Zero reference will happen because clearly the instruction will be rerun and that reference will be set to 1. And then the next page fault will follow through and then come back up to the top to find a 0. Now the thing is, every time the pointer passes over a page that's set to 1, it sets it to 0. So that eventually the entire list will go to 0 if every page has been referenced. Another option is to use 2 bits. We can use a reference bit, as we have been using, and a modify bit if it's available. So whenever a page is referenced, it's set to 1. When it's modified, both reference and modify are set to 1. And then set the reference bit to 0 in the clock algorithm. So what happens now is we base what we're going to replace on the 2 bits. If both bits are zeros, that means it wasn't modified or recently used. This is the best page to replace. If 0 and 1, it wasn't recently used, but it is modified. So this may not be as good to change out simply because we'll have to go through the write operation as well as the read operation. But it's still a good choice because it hasn't recently been used. 1 and 0 means that it was recently used, but it doesn't have any writes to it. So we probably can swap this out. We probably will be used soon, but we could still swap this out. And then if both bits are set, that means not only was it recently used, but it was modified too. So this is one way to manage this. Gives a better idea of what the page is being used for and whether it's a good victim to swap out. There are counting algorithms as well, where we keep a counter of the number of page references. This is not common simply because hardware generally doesn't support this kind of operation. They'll not. Most memory management units are not going to take the time to increment a counter within a page table entry, but it allows us to use an algorithm called least frequently used, which is an algorithm that looks for the smallest counter value and replaces it. You can also do what is called most frequently used. It's based on the argument that the page with the smallest count may have just recently been brought in, and we don't want to swap that out too quickly. Something with lots of with a high counter value could be considered old and ready to be swapped out. So there are algorithms to help with page buffering. So page buffering is where we have a pool of free frames. And what we do is we just, whenever a page fault happens, there's a frame available and we can just simply swap in without having to worry about swapping out. We just simply read the page into the free frame, and then a victim is selected to evict eventually. Doesn't have to be evicted right away, but it's marked for eviction, and it can be taken care of by a kernel process or the kernel itself. We can also use a list of modified pages, and when the CPU is idle, we can go ahead and write pages and set them to non-modified, so that those pages can be more likely to be freed up. We can also keep free frame contents intact. So whenever a frame is freed, such as for a pool, for this pool of free frames, even though it's freed, its data may still be there, and we could reuse that as necessary. This brings us to the end of Lecture 10.4, where we discuss various page replacement algorithms.